Now we'll look into properties affecting the acidity. Before we do that, we'll try putting the conjugate base pairs for this equation, and we'll also see where the equilibrium shifts. Is it going forward? Is it going backwards? So for first species over here, it has a negative charge on it, so that is an indication that it's a base. The other one has to be an acid then. Now you need to figure out the base pairs. Now it's really important that you mention which species making a conjugate with what species, and that's really important, and I'll tell you why. This is a conjugate acid and conjugate base. So if you notice, an acid is making a pair with conjugate base, and a base is making a pair with conjugate acid. Now, why is it important to know that? Well, you need to know that if you have a strong base, the conjugate acid that it's making is going to be weak. Similarly, if you have a weak base, the conjugate acid that it's going to make is going to be strong. And it's vice versa. So let's say you have a strong acid, it's going to make a weak conjugate base. If you have a weak acid, it's going to make a strong conjugate base. So it's it's vice versa, yeah. Now, for this equation, now we'll figure out if it's what is strong and what is weak. Now, that is why we're looking into properties affecting the acidity, but I'll just talk about this charge delocalization factor here real quick, because this one, for this equation, you need to figure out the charge delocalization point. Well, what you need to remember for that point is like whenever you see double bonds, that means that your compound is stable because the charge gets delocalized. That means that um, for this equation, for this species, the first one, this double bond, it can also shift here. This double bond can shift here. This double bond can shift here. And that is the reason why you have a benzene ring, which you just put a circle because the double bonds, they're like always moving around. So that's called charge delocalization. But because of this property, your compound becomes stable. So another thing you need to remember is that if something is stable, that means that it has low energy. If something has low energy, that means that that thing is weak. This is a really important point to remember. Something is stable, that means that it has low energy. That's why it's stable, because if something has high energy, that means it's not stable, because high energy means like it's moving around all the time, right? Just think about particles, you know how if they have high energy, so they're like bombarding together more often. So if you have low energy, so they're stable. They're calm. They're in peace. That's why, so remember, if something has low energy, that means that thing is weak. So for this base right here, now, how do you compare these things now? I can't compare, so you need to compare one base with another base, one acid with another acid. But for this equation, I cannot quite compare my acid with my conjugate acid. The reason being because my acid and my conjugate acid are not charged entities. So whenever you compare, just it's way better for you to be comparing things that are charged. So look for charged entities over here. Well, these two bases, base and the conjugate base, they're both charged. So you can compare these two bases, and that's how you're going to figure out the rest of the equation as well. Basically, you just need to figure out one thing that's weak or strong, and you can just based on that one thing, you can figure out the rest as well, the rest three species if they're strong or not. How are you going to do that? Well, because this base undergoes conjugation, right? Well, conjugation means like the electrons are delocalized. That's just another word you can use. The charge is delocalized here. So that means I said that if charge is delocalized, if you have double bonds, that makes the compound stable. So if it is stable, that means that it is also weak. This base becomes a weak base. So because we were comparing this base with this conjugate base, right? So if this is weak, that automatically means that this conjugate base is strong, right? Because we were comparing two bases. If one is weak, the other one has to be strong. This is strong. Now, if you notice here, this arrow is coming from this acid. Now, this is a conjugate base pair. And what did I say about conjugate base pair? That if one thing is strong, the other, if conjugate, let's say you have conjugate base here that is strong, so its acid is going to be weak. just over here. That's what I said over here. So it's going to be a weak acid. And similarly, if this base is weak, its conjugate base pair, its conjugate acid is going to be strong. And that's it. Like you just figured out that this base is weak, and that's how you figured out the rest of the three things as well. Because of this information, now I know that my products both have something that is both have this element of strongness to it. So that means that your reaction is moving backwards now. So to show that, you will make an arrow like this, and then the other one is going to be like this. So this arrow, like the one that is going backwards, mean that it's longer in size. That refers to the fact that your reaction is more favored towards the backside. So your products are being made. You have more of the reactant. You have more of the product, and they're making the reactant. So it's moving backwards because it's your products are strong. And there is a possibility that these two, your products could have, your reactants could have been strong. If your reactants are strong in comparison to your products, then your reaction would be moving forward. However, there could be a possibility, let's say that this was strong base, this was weak acid, this was strong acid, conjugate acid, right? And this was weak conjugate base. Let's say this was the case. So you have one element that is strong, one element that is weak. So over here you have an equilibrium. So your arrows are going to be of the same proportion, which is just like this. You're not going to make one arrow longer than the other one. That's it. Now we'll start with the first property affecting the acidity, which is the electronegativity. Over here I have two equations. So I'll be comparing this acid with this acid. Well, how do I even know these are my acids? That's because the bromine I'm reacting it with is a base. How do I know that? It has a negative charge. That's how. And this is my acid. I made equations out of it because I only needed the conjugate base here, because conjugate bases are charged for this equation. So I can't really compare the acids together because they're not charged. So I need to make a conjugate base out of them because that's going to be charged. So I can compare the charged entities together. So that means that I'll compare this conjugate base with this conjugate base, and then I'll figure out which one is stronger, which one is weaker. So let's say your one conjugate base is stronger. So that means um, the acid it is made from is going to be strong. Well, if your conjugate base is weak, your acid is strong. So okay, over here I have my oxygen that has a negative charge on it, and over here my nitrogen has a negative charge on it. Now, which one can accommodate uh, a negative charge better? That is what electronegativity means. So electronegativity is which species can better accommodate negative charge. So we know that oxygen is more electronegative. So oxygen is more electronegative than nitrogen. So that means that oxygen can um, accommodate the negative charge a lot better. If it can accommodate negative charge way better, that means that this one is going to be stable. This structure is stable because negative charge is not causing oxygen any problem because it knows it can accommodate it way better than nitrogen can do. So in comparison to this structure, the structure that's below, it's not stable because nitrogen is less electronegative. It does not want that negative charge around it. It wants to get rid of that negative charge. But oxygen doesn't, because oxygen is more electronegative. So that's the structure that's above is stable. So if something is stable, that means that it has low energy. Low energy, that means it is weak. So this structure, because it was a conjugate base, so that means that this structure is weak conjugate base. Automatically, well, this one is going to be stronger than in comparison, right? Because it is not stable. Not stable means it has high energy. High energy means that it's strong. And in comparison to this conjugate base, the acid it's coming from is going to be strong. And this below acid is going to be weak. And that's it. So this is how I know that this acid is stronger. Before we move on to other properties, we'll just look at this question and see which proton is more acidic. Over here, I've marked the protons that we are considering. So because I know that all of them are acids, but if you see I can't, so over here, see I'm not making equations out of here. So you don't always need to make equations. If you have a compound, you don't really need to react with something and make an equation out of it. What you can do is that just the hydrogen that's in question, just remove that hydrogen. So for this structure, it would be like this: the hydrogen got removed. So this carbon gets a negative charge. This nitrogen, this is hydrogen, this nitrogen can get a negative charge. Similar here, this oxygen is going to get a negative charge because what I'm doing is that I'm just removing these hydrogens in question. When I do that, what I'm left with are the conjugate bases because this acid is making a conjugate base. Negative charge is there now. The reason I need to make these conjugate bases here is because my acids were not charged. I need to have a charged quantity to be able to compare which proton is more acidic. Now I need to compare these three structures together, and that's how I can figure out which acid is more acidic. Which, well, it's basically just when it says which proton is more acidic, that's just like basically you just need to figure out which structure is more acidic. Anyways, so we'll start with this one is also dealing with electronegativity, right? Because these are three different structures, they have a negative charge. So you need to question yourself which atom can more accommodate the negative charge that it has. Oxygen can accommodate it way better. So because oxygen is highly electronegative, and then comes your nitrogen, and then comes your carbon. Carbon cannot accommodate that negative charge. So what so remember, something that is highly electronegative would want a negative charge. Something that's low electronegative would be better off with a positive charge. So over here, oxygen has a negative charge, it's happy, but carbon has a negative, it's not happy. So this structure, sorry, let me just grab it there. This carbon with a negative charge, it's least stable because it does not want that. And oxygen, it is most stable here. So if you see that these are our bases, right? Because conjugate bases. So if this one would be, if it's stable, that means it has low energy. So it is a weak conjugate base. And then this is a strong conjugate base. And nitrogen is like the middle ground here. I'm just figuring out the most and the least. So whatever is in the middle, like nitrogen is gonna come in the middle, right? Out of these three. So that means that because if this is a weak conjugate base, this is going to be a strong acid. Because remember, weak conjugate base is going to make a strong acid, and strong conjugate base is going to make a weak acid. So when you number them, so let's say the structure is A, this is B, and this is C. When you want to mark which is the most acidic, so C is the most acidic, and then comes B, and then comes A. C is your most acidic proton over here. This proton was the most acidic. You can also say the C structure is most acidic. That would be correct as well. Now we'll look into atomic sizes and how do they contribute in something being more acidic than the other. We'll again compare our conjugate bases. The reason again being that our acids are not charged, our bases are charged here. So when we compare oxygen with sulfur, we are comparing atomic sizes because because they fall into the same group. Now, if you have a periodic table, remember, let's say over here you have your fluorine. Now remember, fluorine is the smallest in terms of atomic sizes. So that means that if you're moving across the group, the size of the atomic size is decreasing. And if you're moving down the group, atomic size is increasing. And oxygen is placed above than sulfur. So that means sulfur has a greater atomic size than oxygen. So if something has a greater atomic size, that would mean that they can accommodate the negative charge better. So this negative charge is way more suited on sulfur than it's suited on oxygen. So that means that this above diagram is going to this the one with the sulfur is going to be weak because the negative charge on sulfur is stable. If it's stable, it has low energy. It has low energy. It is weak. So this makes a strong acid. Similarly, this conjugate base is going to be strong because this structure is not stable in comparison to the one that's above. If it's not stable, it has greater energy. If it has great energy, it is strong conjugate base. This is going to make a weak acid. Now we'll see how does hybridization affect the acidity of a species. Actually, I forgot to put a negative charge here, but there's a negative charge here. To make it more make more sense, just put carbons over here so that you can understand what's happening. And this carbon had a hydrogen, so this bromine attacked this hydrogen, and the negative charge went to the carbon. Similarly, for the one at the bottom, there was a carbon that had bond with hydrogen. So now the hydrogen is gone, and the carbon has the negative charge. Now, yet again, we'll be comparing the negative species because they are conjugate species and they're charged. That's why. So first, we'll figure out the hybridization of the carbons. Now, again, we use charged species to figure out the acidity, but when we're figuring out the hybridization, which carbon are we going to figure out the hybridization for? It doesn't have to be carbon every time. We just need to figure out the hybridization of the charged atom over here. For the charged atom here is the carbon, it's carbon here as well. So for the one on the top, the hybridization would be sp. How is it sp? Well, for hybridization, we only consider the sigma bonds and the lone pairs. So for the first one, you have two pi bonds, and there's only one sigma bond, and then there's one a negative charge that would be sp. And for the one at the bottom, you have three sigma pairs and one negative charge. So a total of four electron clouds. That would be sp3. Now, what you need to know is that for the one on the top, if you have sp, that means you have 50% characteristic of s orbital and 50% that of p. For the one on the bottom, you have 25% s and 75% p. Now remember, the more S characteristics you have, more stable your species is. So that means that this species will be more stable because it has more of S characteristic. So this is also weak conjugate base then because it is more stable, less energy, weak conjugate base. Automatically, this one becomes strong conjugate base. So for the first one, the acid would be strong. At the bottom, it would be weak because strong conjugate base is going to make a weak acid, and weak conjugate base is going to get you a strong acid. Now we'll look into induction and what does that tell us about the acidity of something, but also what does induction even mean? So we'll look at this compound right here. So induction could be positive or negative. So if it's positive, that means electrons are being given, and if it's negative, that means electrons are being taken. Now, what is something that takes away electrons? That's something that is a nonmetal, which is chlorine over here. So this has a partial negative charge, and where is it getting those electrons from? From CH2. So it has a partial positive charge. But now the CH2 that's bonded next to it would give some electrons to this CH2. So this CH2 gets these two signs on top of it. However, now this CH2 is going to get some electrons from this CH3. This is going to get these three signs on top of it. So basically, electrons are moving towards the chlorine, which is a negative, which is a nonmetal, which needs to take electrons. So electrons are moving towards the more electronegative species over here. So now we'll figure out this part, like which is more acidic here. And what will we do here? Actually, I just noticed my diagram is half complete. But anyways, we'll just do it along the way. For the first one, we have CH3 over here. So I'll just put CH3, but I'll try to make hydrogen so you understand what's going on. Here I'll have fluorine, fluorine, and fluorine. Now remember, the charge is going to move towards something that's more electronegative. So your hydrogens are going to give the charge, the electrons to carbon, and then from carbon it goes to this oxygen. So now if you see that all the charge is going from all these different branches and it's going to just one species, which is oxygen. However, the one at the bottom, the charge is going the other way around. It's going towards fluorine because fluorine has a partial negative charge. So your charge is going from one species and it's branching out to multiple species. So it's going on to all these fluorines. So because in the lower in the diagram that's on the bottom, the the charge is being more spread because it's going into these three different branches, right? So that means that it's more stable. If it's more stable, it has less energy. That means it's a weak conjugate base. A weak conjugate base is going to make a strong acid. However, on the one that's on the top, if you see, the charges are coming from multiple directions, but they're converging into one species. They're going towards one species. They're not spreading apart. So that is less stable. So this is a less stable would mean that it's a strong conjugate base. So this is making a weak acid. And that's it. Now we'll look into charge depolarization. So charge depolarization means that you know how you have a double bond over here. What I usually do is whenever I see a double bond, I know it's automatically more stable because it's gonna go under depolarization. That means that the charge. Okay, so if you look at the bottom at the diagram at the bottom, your double bond, these electrons can shift and make multiple resonance structures. So if you have this, so this, oh wait, this negative charge can come here, and then the electrons on this double bond can go to the oxygen. The oxygen is going to get negative charge, and then this oxygen will make a double bond here because this charge is going to make a bond here. So if you now you see like you have this structure, but now you also have this structure. So that means that negative charge is moving from one oxygen to another oxygen. So because so this is mean that this means that it has a resonance structure. Your electron is your electrons, yeah, is moving from one oxygen to another oxygen. Because that is possible, that makes it more stable. So if it's more stable, that means it is a weak conjugate base. So it makes a strong acid. So this one, because this negative charge is not making any double bond here, it's not going to make a double bond here because it doesn't have any depolarization. So that means that this is less stable. So this would be strong conjugate acid, and this would make a weak acid. And that's it.